Hearty welcome to everybody who's visiting IIT Bombay. Kavi asked me to talk to you about reinforcement learning. I decided to do it in 4 parts. First, telling you what is reinforcement learning, what is the problem it is trying to solve. Following which, I'll do a small dive into the technical aspects of reinforcement learning. Applications, I think the point of today is to also imagine things that can be done by using new technology. So reinforcement learning, what are its potential applications, and then we'll finish up. All right. So what is the reinforcement learning problem? I'll begin with this motivating example. There is this international federation called RoboCup. Okay, it came into existence in 1998, and it has set itself the following goal: that by the middle of the 21st century, a team of fully autonomous humanoid robot soccer players shall win a game of soccer complying with the official rules of FIFA against the winner of the most recent World Cup. Okay, so in 2050, RoboCup wants to have done enough for a team of 11 humanoids playing autonomously to beat the human World Cup champion. Okay, so there's a competition that happens every year. RoboCup meets in the summer. I'll play a video from a few RoboCups back, I think 5-6 years back. Okay, so you can see the humanoids. So, I mean, while you are seeing this, try and identify what is there between now and 2050 if we want to actually be beating the human champions. This is, I think, 2018 or 19. It's about 5-6 years back. It doesn't look too different today. Okay, there have been some improvements. So there's an Australian team in yellow. I think the blue is probably German, because the audio isn't playing. All the commentary I can hear in the background is actually German. This also tells you why robotics is hard. Humanoid robotics, bipeds are particularly hard. Okay, at this point, what's the prediction? Are they going to score or not? Yes, no? Valiant effort from the goalkeeper. Okay, all right, so good. So, I don't know, that makes us feel good, but if you start thinking about the gap that exists between this and having to play human level soccer, right, in literally like 25 years from now, I mean, what is to be done? Of course, robotics is to be done. There are so many aspects, right? The actual physical hardware of the robots. These robots need to be able to like process their sensation better. They are getting input from a camera, right? One camera mounted on their foreheads. They're talking to each other by wireless. There are all these aspects, but the aspect that I would like you to think about, right, in the context of this talk is the following. So each of these robots, for everything it is doing, it is an autonomous agent. It's not getting instructions from outside, okay? It has code, right, that it is executing. Like there is a controller, right, that's been downloaded on a memory stick and put into the robot, and that is literally determining every behavior, right, of the robot that you saw. Now, if we ask ourselves in 2050, right, again, there's going to be a similar program running on that chip. Who is going to write that program, right? How do we create this program? It's going to be, I don't know, 100,000 lines of code or something like this. Now, how do we come up with that? Are you and I, or your students, right, going to sit and start writing if then else rules? If the ball is so far away, right, and this is happening, then you turn a little bit to the right, right? It seems inconceivable that we can think, right, perceive, do cognition in the same space that these robots have to, right? So us getting into the loop and trying to do it seems like a very unscalable prospect. On the other hand, if I asked you a slightly different question, among all the programs that you can possibly run on that robot, which one will you pick? Given a particular program, will you be able to evaluate it, right? Will you be able to put a number saying, this program controlling these robots is so good versus some other? Now, this seems very easy to do, right? We know exactly what these programs to do. The best program that we can put on a robot is one that will maximize the probability that these robots will go and win games of soccer, okay, or football. So, although it is not easy for us to specify behavior itself, right? It is very natural for us to be able to specify what is desired, right, for certain behavior to be achieved. And this is a general theme, okay, of reinforcement learning. So if reinforcement learning is the answer, to what question is it the answer? So somewhat abstractly, right, we think of modeling it as an environment, as an interaction between an agent and an environment. Okay, in this case, clearly the agent was the soccer player. You'll see so many different tasks. We are also agents, right? So what do we do on a regular basis, continuing basis? We sense the world. Okay, so these robots also sense the world, and they have to act. Okay, they have to take actions. In their case, it might mean giving commands to their motors. Similarly for us, right, we contract, relax our muscles, right, we open, close our eyes, do so many things. Other agents, which you'll see like a whole bunch of them in this talk, right, have other actions that they must take. The contribution that the agent makes in between is to decide which action to take. Okay, agents have choice, right? I can either look left or look right, walk in front, walk behind, things like this. And so really the behavior of the agent, right, is specified by behaving how it takes actions in different states. Okay, so what the agent senses is usually called state. What it does, right, is called a decision or an action, and this keeps going in a loop. Now, the way that we can intervene into this setup is to say that certain states are good, certain states are not. Okay, we get in and say, here's the state. If you get to that state, I'll give you like a great reward. If you get to some other state, right, I'll give you like a big negative reward, right, which means a penalty. So, for example, in the context of soccer, imagine giving the agents reward if they manage to score the goal, right, and maybe concede. Right? If they concede a goal, you take away some points from them. And then tell the agent, please figure out how to take actions so that you will maximize your reward. I'm telling you, this is what the reward is. You please figure out how you should be taking actions from different states so as to maximize your long-term reward. Okay? If that is the question and that is what these agents are setting themselves up to do, then they are doing reinforcement learning. Okay? So let's see this with a couple of examples. I'll show you a video, okay, which is pretty much self-explanatory. DeepMind is a company that came into being in the 2010, 12, 13, something like this, right? And 2015, right? They did some work, and that's what you're seeing a video of. This is a game called Breakout. Okay, it's a video game. You can see what's going on. Okay, your agent is controlling this puck, the bottom of the screen. Something is falling according to gravity. And every time, right, they hit one of these bricks, right, you can see this number going up by 1, right? You get 1 extra point, which you can think of as the reward. So you saw 100 episodes of training, now 400 episodes of training, which means it's played 400 such games, right? You can see that it's doing slightly better. It's not losing the puck as easily. 600 training episodes, okay? Basically expert level. And what is remarkable is the learning algorithm that has been used. The only input it has been provided at every point of time is this number. You get 1 extra point for doing this. By doing something else, it wouldn't have got those points. So exactly that paradigm which we had described abstractly is what is being used. You can see with more and more training, the agent is actually improving its behavior. This seems I don't know, like very interesting, right? Something that has broader appeal, but it is also not something that we should be surprised by, okay? We are not new to this. We see it in the animal kingdom. We see it in our own selves. So those of you who have children, right, have seen them learning to walk. Giraffes, within a few minutes of being born, right, do this to try and stand up, okay? They don't like falling, right? They get a negative reward when they fall. Then slowly over a period of time, they figure out how to move their limbs so that that doesn't happen. This is a big positive reward, right? If you can stand next to your mother and be cuddled, I guess if you're a few minutes old, you feel good, okay? So the giraffe has figured out how to do that, okay? So this is reinforcement learning, okay? How did the giraffe do that? How did DeepMind's agent learn to get better with time, right? It would be nice if we can do more and more of that, right? So reinforcement learning is the enterprise of doing this. Okay, so as a field, reinforcement learning, although it's very popular now, has been around in various forms, and it really is at the intersection of multiple fields of inquiry, starting from the work of Pavlov, right? Skinner, these are psychologists. Skinner is the father of what's called behaviorism. who saw that animals can be trained by reward and punishment. Okay, so Skinner did his experiments with pigeons, dogs, mice, and you could give them like rewards and punishments to make them do like interesting things. Like you could get a dog to scale a wall, right, just by slowly like incentivizing to do it. The more modern applications of reinforcement learning depend on a very solid mathematical understanding. Now, the genesis of that is in the 1950s and 60s, particularly the work of Richard Bellman, Howard, right? These are people who worked in operations research, developed a family of algorithms called dynamic programming. Okay, so that is what applies over here. There's folks from control theory, right, which has been around again, I guess, since 60s, 70s. A lot of the algorithmic analysis, right, particularly in the physical world, I don't know, the students here might be more familiar with control, right, is also very related to reinforcement learning. We call it states and actions. The control people will call it situations and controls, right? State S, action A is the same as situation X and action U. Okay, so names are different, but at the heart, right, we are trying to solve the same problem. Much more recently, there's been inputs from wet lab, right? People who have animal experiments. You could get readings from electrodes in brains of small insects and even small mammals. Right, and there is growing evidence that some of the learning mechanisms that we use, right, or humans or animals use, is very similar to what mathematics of reinforcement learning will tell you to do. Of course, I'm standing here as a representative of the computer science and engineering department where we work on AI. So the computer scientists have joined the party, and I think the term reinforcement learning, the textbook, and all of this, I think has kind of been like appropriated by computer science. Okay, but I think it is worth keeping in mind that really, right, there are intersections with all of these fields. Okay, so that's like an introduction to what's going to happen. I'll take the next 5-7 minutes to say things a little bit more mathematically. Okay, what is at the heart of trying to grapple with this problem? So we formulate the reinforcement learning problem using something called an MDP. Markov decision problem. Okay, this is a bit like a graph if you're familiar with graph theory. So here's an MDP with 10 states. Okay, I've called them like 1, 2, 3 through 10. Now, every state, this is an MDP in which an agent has 2 actions to take. From each of the states, it can take either a red action or a green action. Now, the idea of drawing these arrows and putting these numbers is, if the agent takes action red from state 1, then with probability half, it's going to go in the next time step to state 2. 15% chance it'll go from 1 to 6. 35% it'll stay in state 1. Okay. The other action, on the other hand, 1 will deterministically take it from 1 to 3. Okay. This is just an example, but similarly, right, from every state, for every action, there is a transition probability from that state to other states, which is there. Okay. That's a part of the MDP. The other thing that is there is when you reach a state, you get a reward. Okay. Now this reward in this example I've given like -1 for reaching 2, 2 for reaching 6, 10 for reaching 7, and so on. Okay. This is really a description of the world in which the agent lives. Now what is the agent's job? Agent's job is to take actions. Okay. So the agent now comes, it is born in the world, like the giraffe got born. So let us say the agent, when it is born, is in state 1. The question facing the agent is the question facing you and me and everybody else. What to do, right? What should it do? So in this particular setup, the agent has only 2 choices. It can take either green or red. Which one should it take? And at this point, there's really no basis other than maybe green is your lucky color or something like that. So to say that green is the better action. I don't know. When I did this, I guess I chose red. So let's say you choose red, right? And then on account of having done this, the agent now sees that it has actually gone from 1 to 2, and it's getting this reward of -1, okay, in the first time step. Now again, agent has to always do this. From every state, it has to decide what it has to do, right? So let's say this time it again chose red. It went from 2 to 6, got a reward of 2. See, other things could also have happened. Remember that these transitions were stochastic, right? This particular time, this is what happened. But in general, there is a stochastic evolution of the trajectory of the agent. It got a reward of 2, right? This time maybe it did green, it went to 7, it got a bigger reward. And it's going to keep going around like this, okay? Now, of course, the first time you are at a state, you don't know what to do. But imagine, right, there's only 10 states, right? So after, I don't know, 10 steps, you're bound to be in some state which you've already visited, and you know what's going to happen if you take, I don't know, red or green from there. And over time, right, you're going to gather data about this world just by having lived in the world. The question is, how can the agent take actions so as to maximize its expected long-term reward? So long-term reward means the first time steps reward plus the second time steps reward plus third time steps reward. Now this is important, right? Because it's sort of easier to be myopic and say, okay, let me do the thing that gives me greatest happiness right now. Let me eat 10 gulab jamuns, right? But we know that I'm, on account of doing that, going to go to a state in which I'm going to hold my stomach and run to the hospital, right? So the long-term reward of eating 10 gulab jamuns is not great. Short-term, it is good, right? So we are here for maximizing long-term reward. And we're saying in expectation, because these transitions are all stochastic, right? You do exactly the right thing because you were unlucky, right? Something bad happens. So this is a question. And note that given an MDP, right? Suppose I had specified this task with these transition probabilities, rewards, and so on. There always exists an optimal way to behave. Okay, if you knew all of this, you can compute. So if I gave you all these numbers, right, the rewards as well as these, you can actually use dynamic programming to say that, okay, from this, the right action to take is red. From here, the right action to take is green, maybe, right? There will be one such behavior. It's called a policy, which actually gives you like the maximum expected long-term reward. The problem is we don't know these numbers, and therefore we don't know what the optimal policy is. The philosophical question is, even so, right, by living, by gathering data about the world, can we eventually learn how to behave according to an optimal policy? Okay, so that is the question. The great thing is that the answer is yes. Okay, about 30 years back, it was figured out, right, that you could do this. So this is the most mathematical of my slides. It's all of one slide, then we'll get to the applications and so on. Here's an algorithm called Q-learning. So it's a classical algorithm. Remember, our problem had 10 states and 2 actions. So here's what I'm going to do. I'm going to make a table. For each state action pair, right, I'm going to keep a number. Now this number is meant to be an estimate of the expected long-term reward if I take that particular action from that state, right? So if you're looking at 5, red, this minus 4.2 here, I'm intending it to be an estimate of the expected long-term reward if I take red action from 5 and thereafter, right, I act optimally. Okay, of course, you don't know the value of acting optimally, and when you start, right, these values are all going to be off, right? They're only estimates. In fact, usually you'll start with all zeros. But the idea of Q-learning is as you go through your life and gather experience, you will update these values, okay? So in particular, suppose you go from state ST by taking action AT to ST plus 1 at the next time step and get a reward in between. You update your Q value estimate, okay? You will make an update, you'll make a change in this table. This is minus 4.2 will become something else, okay? The particular formula by which it becomes something else is called the Q-learning update rule. It will change by a little bit, okay? But then you do that, right? Again, you go to the next time step, you decide which action to take. Again, do a Q-learning update and you keep doing this. You have to be a little bit, so this quantity here, right, is really the difference between your current estimate of the Q value of SA and a new estimate that has become available because you went from time t to t plus 1, right? You can use your estimate at state st plus 1 as a way of competing, right, with your current estimate and try and reconcile these two. So this is called Q-learning. So this is how you update your Q values when you take an action. But then how do you take action? So most of the time, right, let's say 90% of the time, you should be acting greedily according to your Q table. So that means if you're in state 8, right, what your current estimates tell you is that by taking red, you're going to get 4.8. By taking 9, you're going to get 9.9. By taking green, you're going to get 9.9. So therefore, most of the time, you should be taking green, okay? But of course, remember, these are still noisy values. So you should not be 100% greedy. With some small probability, you need to explore, okay? And doing this in the right way is called balancing the explore-exploit trade-off. The good news is you can do this, right, in a mathematically rigorous way. And how many years back now is this? 30-something years back. It was shown that this will eventually converge to optimal values and to optimal behavior. An agent in the limit, right, in spite of not knowing how the world behaves, can act optimally for that world just from experience, okay? So learning from experience by doing trial and error is reinforcement learning. We saw the giraffe doing it. We saw DeepMind's program doing it. Here is mathematical modeling, right, and a mathematical proof to show that this is rigorous, okay? You can do it. One gap that happens between theory and practice. So here's a table with 10 states and 2 actions, right? In the real world, problems are large enough that you don't have like a small finite number of states. You can have basically infinite number of states, or very large. If you're playing chess, you have 10 to the 40 or 10 to the 80 states. I don't remember the number, but too many for you to store in a table. And so the way you go from theory to practice is to use what is called generalization. So you must be familiar with neural networks. These are modern function approximation schemes, right, of ways of mapping, having non-linear mappings from input to output, right? So the way a neural network is used is, instead of the Q table, you can give the state, right? Remember the breakout task that you saw? The state there was essentially the image that was coming to the agent at every point of time. You can have the actions as outputs, right? The actions are going left, right, up, down, and things like this, and learn this mapping, right, by doing something like Q learning. Okay, so this is the gist. This is, of course, one of many different variety of reinforcement learning algorithms, but this is just to sort of give you a glimpse of what is there. Now, where does this apply, right? We've seen like a couple of examples already, but are there like implications for economic growth, right? As Kavi was saying, as or sort of interesting things that we can do, right? Which more efficiently than we are doing right now. So the answer to that is very affirmative. I'll give you like 5-6 applications I have sort of listed over here. The earliest applications of reinforcement learning were in board games. Okay, in '92, Jerry Tessaro showed that a program that uses Q learning essentially, right, to play backgammon, it was able to achieve like master level play. Okay, of course, backgammon is a smaller, simpler game. This is subsequently extended to much more like complex games. The most recent success, this is again from 8-9 years back, was AlphaGo. AlphaGo was a program built by DeepMind that used reinforcement learning, right, to learn how to make moves in the game of Go. It's a game like chess. It's not played on 8x8. It's played on 19x19. It's very popular in East Asia, Southeast Asia, and so on. Okay, yeah, and it has learned by doing reinforcement learning. Perhaps more relevant to this crowd is the fact that for various control tasks, also you can use reinforcement learning. So Andrew Ng is a name some of you might have heard in the context of him being the founder of Coursera. If you've done a course on Coursera, Andrew Ng was the founder. For his PhD work, he worked on reinforcement learning, and one of the most sort of exciting demos that came out of it was control of a helicopter. Okay, so he had a helicopter model. This is real hardware, real helicopter. I mean, it's not a helicopter in which you and I will go. It's a model, right? There's nobody sitting inside it, and a pilot is flying it from the ground. So they gathered data, right, about how the helicopter, when the pilot flew it, and based on that, right, they logged states, right, actions. So the state of the helicopter is going to be determined by its position, right, orientation at any point of time, first derivatives of that, velocities, right, and the controls would be like controls to the two rotors, right? You control them for speed as well as tilt. This could be a helicopter, it could be a drone, it could be any other robot. Okay, the principles are the same. They have states, right, which you sense. They have actions. In this case, the task was that of getting the robot to hover at a particular point, right? And so the way they fed rewards to this task was they measure the distance between the helicopter and the position it was supposed to hover. Okay. Now you want that distance to be small, right? That distance is going to be small if you're hovering. It's going to be large if you're away from that point, right, or going up and down. So the negative of that distance, or maybe the square of that distance, is what they gave as the reward. Reinforcement learning picked up, right, how to get this robot to hover, okay, in space. Planning and scheduling is another big sort of area where reinforcement learning is used. Here's a classical paper for elevator control. Okay, if you're in a building with multiple elevators, right, you press the button. Have you thought about, I mean, while you're waiting impatiently, have you thought about the algorithm that decides which elevator is going to come and stop at your floor, right? There's 3 or 4 of them, right? Which one's going to come? So from the building's point of view, right, it is in their interest to not waste too much energy, right? To sort of operate minimally the number of elevators, but at the same time, they can't keep you waiting forever, right? So they need to have a trade-off between wait times, between the call, right, and the elevator servicing, and the actual energy, right, spent for running the whole system. So for example, I mean, if there's an elevator going up, right, there's 20 people on a floor below, right, who are pressing the button. There is one person on the floor above who's pressing the button, right? Should it go up or down? I mean, it's not easy for us sometimes to do the math of these things, but machines do math well. Okay, so if you set it up as a reinforcement learning problem, it will come up with a better policy. Okay, there are other planning and scheduling tasks. Some of my own work is for railway scheduling, right? On a particular track, there's only one track, so there are two trains competing to go on this track. Which one will you let occupy the track? This is an important problem in Indian railways where there are many single line sections, right? Now, this decision is also non-trivial because it's going to have a cascading effect, right? One train might have to go all the way from Mumbai to Kashmir, right? Another one might be a local train. So when you take an action, right, it can't just be based on myopia. You need to have like the big picture in consideration. Reinforcement learning can do that also for you. Here's a very interesting application in healthcare. Okay, so this has been demonstrated in lab on slices of rat brain. Okay, not human brains yet. But what is epilepsy? So you have an epileptic attack when there is uncontrolled electrical activity in your brain. Okay, when sort of, I mean, there is electrical activity in our brain right now, right? That's what lets our like nerves communicate and things like this. But when it's sort of all like the floodgates open and there's electrons firing all over the place, that's an epileptic attack. So one way of treating epilepsy, at least an experimental procedure, is to forestall it, right? To preempt it by giving preemptive like stimulation, electrical stimulation, by having a sort of device in the brain, just like a pacemaker. Okay, so it will keep giving like a small voltage, let's say every 1 second or something like this, and that, right, prevents like the big bad event from happening. But over a period of time, the bad thing about giving like a 1 millivolt signal is you're still giving enough. If you integrate the whole thing, right, that's a lot of electricity that's going to kill your cells and do bad things. So how do you minimize the amount of stimulation while also minimizing the occurrence of epileptic attacks, right? Again, you can formulate this as states, actions, right, reward, solve it, right? So this is again from 15, 16 years back. So I'm giving you some of the classical applications because a lot of original work, right, has happened through the years. I'm sure there are more modern implementations, variations around these themes. Finance, okay, we're sitting in Mumbai, right? So money moves, I mean, here it also moves everywhere else. But the basic problem of should I put money in this stock or that stock, right? I have 40% here, 60% here. Should I keep my portfolio the same or should I reallocate? Again, given enough data, right, about how stock prices have moved, right? Other important variables, reinforcement learning can be used to decide how to do portfolio allocation. In fact, now there are entire tracks and conferences, right, for using reinforcement learning in finance and so on. Okay, again, right now who's doing stock trading, right? Historically, it has been human beings using their cognition to decide, right? But we have biases, right? We have various sort of like idiosyncrasies. We can't, I don't know, compute so well. Today, you will not expect a human person to do multiplication of 100-digit number with another 100-digit number, right? You know that a calculator can do it, right? And you don't feel bad about it. We got used to that. But it's also true that there are other problems where computation really can make the difference, right? About you making a slightly more optimal decision. So reinforcement learning in this particular case gives you the apparatus for using that. This is a computer. Inside of this is a motherboard. There's a memory system. Okay, so here's another example. I think this is work from Microsoft Research. So there are two major operations you do with a memory: read and write. Okay, there's a whole bunch of programs running, right? Some of them will want to read something, some of them will want to write. Now, you don't necessarily have to do reads and writes in the order they came. Okay, you can reorder up to some point. Okay, if somebody wants to read something that has been written, you can't do that in the opposite order. But sometimes there is the dependencies are not there, right? Now, which is more time consuming, read or write? Read. Read is faster. Okay, write means you have to sort of change the contents of the register and so on. So write takes more time. So you can actually optimize for time and throughput by reordering the instructions. Okay, so here the queue, right, sitting in front of the memory on a bus is essentially like going to give rise to the state. The actions are which of these instructions am I going to execute. You can use reinforcement learning again, right, to learn to do this more optimally. LLMs, talk of the day. I'm sure many of you sitting here are running ChatGPT for something. Here is, I don't know, just a picture, right? You give a query, a prompt to an LLM, tell me a story, and then the LLM does something and it starts spilling out a story, right? Once upon a time, what's going to happen? Now, you can think of an LLM essentially as a policy, okay, which at any point of time, the state of the LLM is what it has already done so far, right? It got this query, right? Various things happened inside it. It had activations for various things. And then it has started generating these tokens. The actions are the tokens themselves. So literally, what is an LLM? A language model is something that will, given, I don't know, something you've already uttered, predict, right, what is going to come next, right? So these English word tokens, right, are literally the actions over which the LLM can choose. It has to choose them properly, right? So typically, the first stage, at least, of training LLMs is somewhat different, right? It is not using reinforcement learning. But what has been discovered is that if you further refine, right, the operation of an LLM, the training of an LLM, using reinforcement learning, you can do better. So many of these big companies, right, have hired, in fact, human experts. They log your data, right? Sometimes when you use it, right, you are asked, is this a better response or is this a better response? So these kind of comparisons, right, between responses go in as the reward, right? And reinforcement learning is run on that, right, to fine-tune the LLM to generate slightly better responses. This is sometimes called reinforcement learning with human feedback. You might have heard this term. If we have to summarize, right, what's going on over here, here is the whole point about reinforcement learning. We live in a world in which agents are becoming more and more autonomous, right? There is incentive for us to automate things, let agents do the decision making. Now, if that is the case, right, it has to be, and you want to scale it up, the more plausible way of doing it seems to be to let the agents do it themselves, right? We can't be sitting in their brains, right, and seeing as they see and doing as they do to decide what to do. So it is easy for us, right, to specify goals, right, specify for an agent what it has to do, and then let the agent figure it out itself, okay? And the technology for figuring it out itself is called reinforcement learning, okay? So that's what we have seen. I've given you a glimpse of the theory. It is by no means like new and something exclusive to CS and AI. It really has been fertilized by many different fields over the years, starting with our observation that animals do it. Much more recently, so by the way, I did my PhD between 2004 and 2011, okay? At which time reinforcement learning was this great idea. It didn't really have so much value in, it had not entered common discussions, right? It was not there in everybody's homes as it is today. Now, to a large extent, that has happened because in the last 10, 15 years, neural networks have really gotten a boost, right, as very effective methods for learning these nonlinear relationships. We've figured out how to do it. We finally have the amounts of data and compute to train these systems. So coupled with neural networks, some of these big successes like the video game that you saw, AlphaGo. One thing that I did not include here is self-driving cars, right? Self-driving cars, they learn how to drive to a large extent by doing a large amount of it in simulation. Okay, many of these companies have simulators. The car keeps driving around forever. Also in the real world, but much more in simulation. Yeah, I hope I have impressed upon you that the field of applications is very wide. Okay, you have like real world, you have simulated, you have finance, you have healthcare, right? So you have to think very open-mindedly. So many problems can be nicely modeled and solved as reinforcement learning problems. If you want to go more into it, of course, talk to me today. But the textbook by Sutton and Bartow has, for the longest, been the sort of Bible for reinforcement learning. 1998 is the first publication. The significant revision happened in 2018-19. Incidentally, I think it's worth announcing that the winners of the ACM Turing Award, which is the highest award in computer science for 2024, for last year, was given to Andrew Bartow and Richard Sutton. Okay, so they've really been the pioneers who took this forward, and after so many years, they have been given this very well-deserved recognition. If you don't have so much patience to read an entire textbook or even, I don't know, 1/3 of it, read this tutorial by Kelbling, Littman, and Moore. It's like a 40, 50-page journal article, which again has all the moving parts. Ravi, right, Ravindran at IIT Madras has a course on NPTEL. Okay, he also teaches the course at IIT Madras. That is another good resource. I teach a course here at IIT Bombay. During pandemic, right, I decided that, I don't know, my lectures, videos, and so on will go online. So I've given here a link to my own course web page on which you'll find like lots of useful resources. In fact, let me just show you. Okay, so there's a whole bunch of papers that we read. So by the way, I've not really included references in this slide, but you'll find all of them on my course web page. We have a weekly schedule, right? One after one after one, we present all of these topics in sequence. There are videos, there are slides. There are exams if you want to also like side by side do some exercises and solve them and so on. So yeah, feel free to use that resource as well. And as a student, right, or somebody trying to get into this, what is the background framework you need to have? So I would say, like, although these are not like hard prerequisites, you can be most, I think, efficient about going about this if you're familiar with probability. Okay, the math that we need for this to a large extent is expectations, right, random variables and so on. So that is something that it is good if you already have familiarity. Algorithms, right? How do you prove that a particular procedure is correct? How much complexity does it take? This is again something that we have teach at the in the undergraduate curriculum in the department. But algorithms is another subject that is very relevant here. Being able to do, right, not just have an idea, but being able to take it and implement. At least the interns here, I'm sure that's what they're doing on a regular basis. So programming, you could do C++, Python, language doesn't matter, but being able to program, take an idea and translate it into code, that is something that will help. Okay. All right, with that I will conclude, and thank you.